Okay, thank you very much for giving me an opportunity to talk about our HSC Year 3 week lensing cosmology results. So that were out back in beginning of the April. So it's just 1 month first. So I'm talking on behalf of the Hypers Prime Cam SSP collaboration. And so actually lots of people contributed to this analysis. So especially I would like to highlight the people with these stars. So they are our junior members who played a very important role in this analysis. And let me first show the key papers for the these analyses. And so you can see like 3 supporting papers where it's more technical, like a PFP, like a shape measurement, PSF, and a photosy. And then these are cosmology papers. So since I'm covering the in total 8 papers, so I cannot really go into details. I will skip some details. So if you are interested in, you can make a question where after the talk or maybe during a coffee. And so let me start with SI tension. So the SI tension is recently emerging. So from the CMB primary CMB measurement, so if we assume the lambda CDM, S8 is around 0.83. And but other large scale structure measurement below redshift 1, including the weak lensing and also galaxy clustering and the clusters. So they tend to prefer smaller S8, like a 0.76 or 0.76 or 0.77. So this difference is not really significant yet. But this might be a smoking gun of the breakdown of the lambda CDM. So people are now really looking into the details of these analysis, like including, especially like for LSS measurements, systematics are really challenging. And so for HSC, I will talk about the weak lensing part, and then I will feature some our analysis which tackles that systematic issues. So why a large scale structure of the universe is useful for the testing lambda CDM. So as you can see, well, I don't have to maybe explain, but on the left panel, you can see the simulation with a dark matter and with a dark matter. So without dark matter, you cannot see any structure. So dark matter is necessary to form the large scale structure. And then, so if we do not have a dark energy, the structure of the universe will be more clumpy. And with the dark energy, so the structure is more blurred. This is actually what we are observing. And but anyway, like for measuring the large scale structure, you have to keep in mind that 85% of the matter in the universe is a dark matter. So just by looking at the galaxies, I mean galaxy distributions, we cannot directly observe dark matter, and then we cannot measure the large scale structure so precisely. And then, so one of the major technique to measure large scale structure is weak gravitational lensing. So I don't have to explain details, I guess, but anyway, let me go through this equation. So here is observer, and then here is intervening matter, and here is a source galaxies. And then the light from the source galaxies is bent by the gravity around this intervening matter. And so as a result, the intrinsic galaxy image looks like this in observed plane. This is shared, so it's called gravitational lensing. And then this sharing is denoted as this gamma. And then this is proportional to the geometry of the universe. And so this is a distance between us and distant galaxies, and us and the intervening matter, and the intervening matter and the distant galaxy. And also it's of course sensitive to the matter density fluctuation. This is what we want to measure. This is a large scale structure information. So anyway, so the point is that this is caused by gravity. So there's no distinction between the ordinary matter and dark matter in the weak lensing signal. So we can observe the ordinary matter plus dark matter distribution. And so because this is a talk about measurement, so let me clarify what is observables. And so this weak lensing shear is actually average of the galaxy shapes. So measuring galaxy shapes is actually tricky because we are using a very faint galaxies, and then it's not really large compared to the PSF. But yeah, about maybe 15 years ago, community are not really comfortable or convinced that we are having a good galaxy shape measurement method. But since then, there are lots of progress. So we are more convinced. We're not completely. We have to do a lot of things still for LSST, but we are more comfortable about the shape measurement part. And the other observable is redshift. Here is a redshift. And then so this redshift, especially like if we use photometric data to estimate a redshift, which is called a photometric redshift. So this is really, I mean, like, so this measurement is not, how to say, like this measurement is really difficult, and then it can be measure systematics. So now people are more caring about photometric redshift estimations. So let's keep that in your mind. And okay, so let me jump into the Subaru hyperspectrum CAM. So well, the Subaru is at the summit of Mauna Kea, and because of that, we have a good thing like a 0.6 arcsecond, and it has 8.2 meter primary mirror, and it has a prime focus. So this is a unique point of the Subaru telescope. There's only one telescope with a prime focus, such a large mirror. And so we put the HSC at the prime focus, and then we can get a really large field of view. And then so this is this covers like a 1.7 degrees diameter, and it's covered by about 100 CCDs. And using the HSC, so we conducted the Subaru Strategic Program Survey. And so this is well, the Northern Hemisphere, which shows the HSC survey region. I will focus on this wine red region, 3 regions. So this is called a wide layer of the HSC. We did also a deep and ultra deep for the galaxy science. But the wide layer is mainly for the weak lensing cosmology. And then it's about 1,100 square degrees. And the limiting magnitude of I-band is 26. So it's quite deep compared to other competitive surveys like KISS and DES. And it overlaps with the other major surveys like SDSS BOSS and ACT, and the other spectrum surveys that is used for the calibrating photography. And the survey started in 2014 and then was completed in 2021. But in this talk, I will give a result from the data taken until the April 2019, which is a 416 square degrees. And so, as I said, the shape measurements are important. So we did a really careful construction of this shape catalog. So that 400 square degrees is divided into the 6 fields, like shown here. And then, So we created a shape catalog based on the images of the I-band. So the magnitude cut is 24.5, and the area is again for 16 square degrees. And the number of galaxies we got is 25 million galaxies, and the number density is about 20. This is the effective number density. And the thing is again like 0.6 arcsecond. And then also these shapes, measured shapes are calibrated with image simulations that mimics HSC observations. So this is actually led by the postdoc at CMU, where at that time he was a grad student at the University of Tokyo. But yeah, so this work was led by this very young rising star guy. So yes, so let me show the results from the cosmic shear measurement. So for those who are not familiar with the cosmic shear is a autocorrelation function of the shear of the galaxies. So this is sensitive to the dark matter power spectrum, matter correlation function. So we can do the analysis in two ways. First is a real space analysis. This is called Xi plus minus, and then the Fourier space analysis. This is CL. And also like if we do the tomography, it gives us more information about the evolution of the large scale structure. So we use the 4 redshift beams to measure the evolution of the large scale structure. So this is our redshift distributions we used. As I said, we used the 4 redshift beams, like 1, 2, 3, 4. And gray is photosy inferred by one of our photosy method called by DNNZ. And red is a joint analysis combines the clustering redshift and also other photosy method. And yes, sorry, I should have mentioned what the clustering redshift first. Okay, so this is a clustering redshift where we used the red magic-like sample. So now it's called a Camilla LRG. So Camilla is a cluster finder, like a red mapper. And then red magic is, the red galaxies used for the red mapper. And then, so we use a counterpart, similar thing in HSC, like it's called a Camilla LRG. And so, right. And so this is, you can see like, for this Camilla LRG, because we have only up to Y band, so and the LRGs are red galaxies. The redshift estimate is reliable only up to the 1.2, and then we cannot compute a clustering redshift above this point. So, but the first 2 redshift beams. So our measurement matches very well, photosy matches very well with the clustering Z, and then we are confident, and then we use the Gaussian prior for the photosy shift parameter. This is a nuisance parameter, and derived from these measurements. Like this is a 0.02. It's similar to the width, similar widths compared to the other surveys, DS and KIDS. But for the third redshift beam and fourth redshift beam, so it's not, third redshift beam is partially covered by the clustering redshift, and fourth redshift beam is not entirely covered by the clustering redshift. So what we did is we did a really extreme, like we put this photosy shift parameter like -1 to 1. So we assume there's no redshift information from beam 3 and beam 4. But anyway, so this is our analysis setup. And then so here is a measurement. I don't go to really details, but right, for small scales, of course, I did lots of tests for the baryonic effect. And then we ended up with a similar scale cut with DS. We actually use the Cosmo-Olds to test the impact of the baryonic effect. And then we define the scale cut where we are not affected by that Barank effect. And well, upper limit is actually, sorry, maybe it's not shown here, sorry. Anyway, upper limit here in this free space is from the B mode signal. I mean, we found a non-zero B mode signal around there, so we decided not to use that scale. But anyway, so this is a result, cosmological constraint we got. So from the real space analysis, we got this blue contour, and then the Fourier space analysis, this green contour. And yeah, they are consistent with each other. And we compare that with the Planck analysis. And as you can see, like there is some tension between our constraint. I mean, it's in blue, and also other constraints from the DS and KITS. It's not still significant, but it seems that there is a tension. So this is like 2 sigma level in our HSC analysis. And right, so let me make a comment on that the photo Z shift. So as I said, we use a flat prior for the -1 to 1. And what we found is that the best fit value gives us this number. Like delta Z3 is like -0.12, and delta Z4 is like 0.18. Well, this can be still within noise fluctuations. So we did the mock analysis. Like in this mock analysis, data vector does not have any photo Z shift. But we have used the covariance we use for our analysis. So as you can see, like no blue points are close to this real data. So that means the real data is really, I mean, prefers strongly the photo Z shift. Again, so this is a negative, so it's kind of confusing. So our definition is like if it's negative, the 2 redshift mean this means 2 redshift goes to higher redshift. So this result suggests that this shift can happen. This shift is inferred by the cosmological constraint, by the cosmology analysis. So the important thing is that we made this decision before unblinding. So before unblinding, actually we did some analysis with a more stringent prior, like a narrower width of the Gaussian prior. But yeah, what we found is that we found a significant shift in S8. At that time, of course, it's blinded, so we didn't see the central value of S8, but we did see the shift of the S8. So we thought that something is happening in the photo Z. Before unblinding, well, it's okay. Like even if like S8 is a really crazy value, like a 0.6 or something, we will publish that result as it is. And then we unblinded and then got that result. Like again, like this is S8 is like 0.5, 0.76. So right, so let me go to the next topic. So this is a 3x2 point analysis. Okay, so the 3x2 point analysis is combining the cosmic shear plus 2x2 point. So by 2x2 point, I mean the combining a galaxy-galaxy clustering and galaxy-galaxy lensing. So that means like a galaxy-galaxy clustering is like a special clustering of these galaxies. And then the galaxy-galaxy lensing is a dark matter measurement of dark matter distribution around these galaxies. And then, well, galaxy-galaxy clustering itself cannot give us a cosmological constraint because there is a bias against underlying dark matter distributions. But by combining these two probes, we can break the degeneracy between that bias parameter and set. So that's why it works. And right. And then we perform the two analysis, like large scale and small scale analysis. But in this talk, I will more focus on the small scale analysis. Anyway, so this is some data we used. So for the tracers or GG clustering, so we use the SDSS both sample shown in this orange, and then we divided those into 3 samples. We also applied a luminosity cut to get a nearly volume limited sample, and for measuring the galaxy lensing and cosmic shear, we used this galaxy sample from the HSC shown in blue. And so this is a single, again, this is a single source sample. I mean, just one redshift beam. So this is the point I will explain later. But this configuration is quite different from our cosmic shear analysis. And then our analysis is well, relatively independent. And so yes, so this is a measurement. So actually, Surhud wrote a paper on this. And I don't go to the details, but just let me mention that we go to for the small scale analysis, we go to the 3 megaparsec, sorry, 2 megaparsec for clustering and 3 megaparsec for lensing. And so for small scale analysis, so it goes into the quasi nonlinear scale. So it's difficult to model this. And also there's unknown galaxy physics coming into. And then to cope with that, we developed a model, sort of the kind of the hybrid, like a numerical and also analytical. And so we're starting from the cosmological parameters. First, we predict the halo and halo matter correlation function, like halos shown here. And so this is predicted by actually the emulator based on the n-body simulations. So this solved the issue of the going to the nonlinear regime. And then, so we convolve this output with HOD prescription. So that enables us to marginalize unknown galaxy physics by marginalizing that HOD parameters. And then we can get the galaxy correlation function, galaxy matter correlation function, then project that to the 2D, and then we can get the clustering and lensing. So yeah, this was actually used in year 1 analysis, but we use the same method for the year 3. And also the photo-Z, like as I said, like around this redshift range. So same as cosmic shear, like we do not have the good reference clustering Z. And good reference for the clustering Z. And then we again assume that this uniform prior, that means we do not have any redshift information for the source galaxies. But point is that it can be self-calibrated using the multiple lenses, as long as we assume the lambda CDM. So the evolution of the sigma 8Z is it's constrained by our lambda CDM assumption. So we can self-calibrate this redshift. Yeah, so this is what we did, and then so this is the result of the analysis, small scale analysis. So we got this constraint, and in this case, this redshift shift is not really large. It's consistent with 0, but still negative. And so the tension with Planck is 2.5 sigma. And okay, so let me summarize all the results. So this plot shows the results from the HSC 3x2 point large scale. I didn't explain this, but in gray and in blue, the small scale analysis of 3x2 point. And then green is a cosmic shear real space, and red is a cosmic shear Fourier space. So they match with each other quite well. But well, how often this can happen? And if this kind of matching. I mean, it might be matching too much. I mean, too consistent. So this kind of thing is now being evaluated by the follow-up paper. And we saw our constraint is about 4% in this direction. And also the tension with tension to the Planck is at 2 to 2.5 sigma. So we tried a different tension metrics. And then, so this is a S8 plot I showed in the introduction. And then, so I added when we added our analysis, so it looks like this. Still, yeah, it's preferred the small S8. And the future is like we completed the full HSC survey, so it's about 1,100 square degrees. And then data reduction is now being processed at NLJ using the latest Ruby science pipeline. And then, but in this regime also, we will face some systematic challenges like listed here. So yeah, since I'm running out of time, I stop here.
Thank you, Hironao, for the nice talk, and congratulations to HSC for the beautiful result.
Thank you very much.
Are there questions?
Thanks for the nice talk. I was wondering about, in the starting you have shown about like if we simulate with dark matter and without dark matter, is it essentially open universe or in the second slide? Yes,
yeah, this one. Okay.
So in this both of these cases, when you say like with dark energy, without dark energy, and with dark matter, without dark matter, so is it is the geometry assumed to be flat or?
Yeah, to conserve the geometry, just you know, the fluctuation is assumed to be 0, but the background, background cosmology evolves as if there is a dark matter. So this is a configuration of this simulation. I didn't run that, but this is what this Naoki Yoshida told me.
Yes.
Joe?
Okay, beautiful results, great talk, thanks. I'm wondering if you have had time to think about this Angulo result where he sort of did a reanalysis of DES and basically found that the tension with Planck was weakened if he used a somewhat different nonlinear power spectrum model, and maybe it also had something to do with intrinsic alignments, a slightly different. I mean, all the shifts were small, but it basically weakened the tension. Have you looked at that from an HSC perspective? Would that have any impact?
Right. So, for example, we tried a different intrinsic alignment model, like for this economic shear analysis. We tried our fiducial. Sorry, I forgot which is fiducial, but we tried the NLA and the TAT model, and then we didn't see the significant difference. And this is what we found for the cosmic shear measurement. And for the 3x2 point, because we have a very, conservative, we applied a very conservative cut to select the source key axis. There's no intrinsic alignment here. So yeah, and also, well, for Paranjape effect, as I said, we did a very conservative cut. So I didn't mention that about the 3x2 point, but for 3x2 point, for example, we assume the very extreme case of baryon feedback, like original illustris. It's pretty large. But our scale cut is robust against that extreme case.
Yeah, so my question was actually about this slide. So, so the reason why you cut off at red, so when you're using the spectroscopic sample from Bose, you cut off at 0.7. The reason for not taking spectra above this redshift is because you want to avoid correlation?
Well, we could in principle, for example, take a E-Bose LRG sample, for higher redshift. But before doing this analysis, we did a very quick Fisher analysis. At that time, E-Bose LRG didn't have a complete overlap with HSC, if I remember correctly, Surhud, correct me if I'm wrong. But we looked into we did a quick Fisher analysis. and we found that we don't have lots of gain from that using the EBOS. And if we use EBOS, for example, yeah, as you said, like there's an overlap here, so we would like divide this source sample into 2. So we also consider that option, but in that case, even in that case, according to our official analysis, there's not much gain. So
okay, and the reason for just not taking galaxies between low Z and C-1?
Sorry, what?
I mean, there is a gap between low Z and C-1. Why you didn't take galaxies at those redshifts?
I guess I don't really remember, but low Z is defined to up to 0.43, right? So by definition, low Z
actually, it's like a constant definition now. That low Z and CMAS, it was like an all targeting thing. Now it's like the whole thing from.
Yeah. This is a low Z CMAS TOT sample, right?
Right, but this is the DR12.
Yeah, this is a DR12. So ours is a DR11. Yeah.
Let's maybe postpone some of those more technical discussions to coffee, so that people who are really interested in the nitty-gritty details.
Yeah, I can tell you why we used the DR11 instead of DR12 later, where Surhud actually did that work. Anyway, so.
Okay, let's thank you now again.